Electric charges, just like gravity, act over a distance. Two particles do not need to be in contact for the electrical force of one to act on another. We can use the idea of a force field to describe how an object is being affected by specific charges, and this is called an electric field. The first thing to keep in mind that since a force is acting, then an electrical charge can be represented as a vector. Say we have a positive charge represented by a capital Q. Because Q is a charged particle, it can exert an electric force on other charged particles, and we can represent this electrical force with a vector. Now, depending on the strength of Q and the strength of the other charges, different vectors may be needed. This point charge will exert the electrical force in any direction that another charge might appear. So we can draw this force in all directions and represent it as a field that surrounds the charge. Essentially, this is a way to visualize the electric force that can act on any other charges at any given point within the field. According to Coulomb's law, the strength of the force for the point charge, big Q, acting on a test charge, little q, depends on two things: the size of the charges and the distance between them. In this case, the Coulomb force field is caused by a positive big Q acting on a positive little q. Since both charges are positive, the force acts to repel little q at some force, F1, away from big Q. In another situation, if little q is negative and larger in magnitude, the Coulomb force field will be in the direction towards big Q with a larger force. Now, when we talk about the electric field, we are talking about the force felt by a charge divided by how big that charge is. This gives us units of newtons per coulomb. Now, it is defined using the little q, which has such a small charge that it would not have an electric field. This is so the electric field depends only on the big Q charge and not on the little q test charge we are using to determine it. This makes sense because if the test charge were very large, then we'd be getting into infinite electric fields, and we would have to change our definition of an electric field. We can rearrange this in order to describe the amount of force on a charge in an electric field. This is just going to be the magnitude of the charge times the magnitude of the field. If the charge is negative, then the force on the charge will act away from the direction of the electric field. And if the charge is positive, then the force on the charge will act in the same direction as the electric field. If we want to determine the strength of the electric field, we can substitute Coulomb's law in for the force. The magnitude of the test charge cancels out, and we find that the magnitude of the electric field is equal to Coulomb's constant times the magnitude of the point charge divided by the distance squared. So the strength of the electric field depends only on the point charge, big Q, and the distance. So we can calculate the strength and direction of an electric field due to a point charge of 2 nanocoulombs at a distance of 5 millimeters. Well, we know how to calculate the strength of the electric field, and we know R, and we know Q, and we always know K. So this is simply a matter of plugging in those values into our equation. But we want to pay close attention to our labels. Nano is a prefix meaning 10 to the negative 9th, so we can just add that on to the end of our 2. Milli means 1,000th, so it can be represented by 10 to the negative 3rd. Working all that out gives us an electric field strength of 7.19 times 10 to the 5th newtons per coulomb. This value is positive, so that must mean that the field is pointing away from the point charge. And keep in mind that this field strength exists at any point that is 5 millimeters away from the point charge. Something else we might be concerned with is the force being exerted on a given charge by this particular electric field. The strength of the electric field was defined as the force on a charge divided by the magnitude of that charge, so we need to do a bit of rearranging in order to solve for the force. We just found the strength of the electric field, so all we need is the strength of the charge in question. It is given as negative 0.250 microcoulombs. Micro means 1 millionth and can be represented as 10 to the negative 6th. So plugging this in, we find a force of 0.180 newtons of force. Since our charge was negative to begin with, then the force must be acting in the opposite direction to the electric field. This is expected because we have two opposite charges, and we would expect those charges to have an attractive force. Interestingly, the charges in this example are fairly typical of static electricity we find every day. If you've ever experienced static cling between two materials, this would be a good estimate of the magnitude of the attractive force. So let's look at our positive point charge. We know there's an electric field emanating out from all directions. If a small positive test charge is brought into the field, we can show the vector for the force acting on that charge. This particular force acts in the direction away from the point charge because they are both positive. The test charge is kind of close to the point charge, so it gets kind of a medium force vector. If we take another small positive test charge in another part of the field, there will be an electric force acting on it in the direction away from the point charge, again because they are both positive. However, the test charge is further away from the point charge and so has a bit smaller force acting on it than the first test charge. So we represent it with a smaller vector. And we can keep doing this. Points that are the same distance away from the point charge have the same magnitude vectors. The further away from the point charge, the shorter the vector. The closer to the point charge, the longer the vector. Eventually, we get a map of the strength and direction of the electric field. In this case, both charges are positive, so the field points away from the point charge, and the vectors show that the strength diminishes as you get further away from the point charge. By convention, we usually do not draw individual vectors as they move away from the point charge, but instead draw continuous field lines radiating out from the point charge. Now this looks a little bit different if the point charge is negative instead of positive. We still add in our small positive test charge, and all other things being equal, the only difference is the direction of the force. In this case, the force will move in towards the negative point charge. Now what if we increase the magnitude of the test charge? The force caused by the electric field will increase. To show this, we simply draw more force vectors in our field representation. Now the previous diagrams have shown a simple representation of an electric field when one test charge enters the field of one point charge. You might imagine that in many situations there are multiple charges and their attractive forces to deal with. Since electric field is represented by vectors, we can use the vector sum of the individual fields to determine the overall electric field in any given situation. Say we have a point O that is being affected by two separate point charges. One point charge Q1 is located 2 centimeters directly south of O and has a charge of positive 5 nanocoulombs. The other point charge, Q2, is 4 centimeters directly east of O with a charge of positive 10 nanocoulombs. Since electric field is represented by a vector, we can set our point at the origin of a coordinate system and add the vectors of the point charges into the resultant vector to determine the magnitude and direction of the overall field effect on point O. So the first thing we need to do is determine the electric field of each point charge. We can do this with our electric field equation since we do know the charge and the distance to each point. And we end up with the electric field strength of 1.124 times 10 to the 5th newtons per coulomb for the first point charge and 0.5619 times 10 to the 5th newtons per coulomb on the second point charge. Both of these point charges are positive, and since we are not given the charge of O, we can define it as positive as well. In reality, it doesn't really matter which way we define it as long as we understand that the field can move in all directions. Now that we have our vectors, we can draw those into our coordinate system and represent the magnitudes and directions of the electric fields of Q1 and Q2. Since the direction of the electric field is positive, then the vectors will point away from the positive charges that create them. So if you are standing on O, facing north, Q2 would be on your right. The positive force would push you away from Q2 to the left. So the vector for Q2 will be drawn to the left of O. The same thing works for Q1, and it will push O to the north. When we add the vectors head to tail, we find that they form a right triangle. So the resultant vector forms the hypotenuse of the two initial vectors. This is nice because all we have to do is solve for the magnitude of the resultant by using the Pythagorean theorem. The total magnitude of both electric fields is 1.26 times 10 to the 5th newtons per coulomb. Now we just need a bit of trigonometry to find the angle of the force. Tangent is the opposite over the adjacent, and we find 63.4 degrees. So based on the strength and location of each charge, we can find that the overall electric field points 63.4 degrees to the north of west with a magnitude of 1.26 times 10 to the 5th newtons per coulomb with respect to O. And this is important. We have defined our direction in terms of a certain point. If we were wanting to know the electric field at a different point, we would have to recalculate for that point. As you might imagine, there is no possible way to find the electric field for an infinite number of points. So when we get into drawing electric field lines, we will use a little bit of calculation and a little bit of estimation to draw our electric fields.